other situations where you can talk about these sorts of things. So that's why my presentation is about shellcode and stuff, because I figured it's one of the only good opportunities to talk about it. So I'm going to talk about some recent research that we've worked on and other people have worked on. We're also going to talk about some older things that I think are really interesting, and even people who do this sort of thing don't know necessarily about them all. So I want to cover some of that stuff and just some like new tricks and techniques and stuff like that. So one note here is that I probably have too much material even to fit into an hour, so I'll probably cut some of it out. And I also have a lot of just random stuff on my laptop, examples and stuff like that. So if anybody has any questions, anybody has any certain types of things they want to see, just feel free to ask, and I'm sure I can explain it or like show some examples of it or something like that. So I want to start with a simple. This is my diagram. I'm going to slowly build up upon it. So I'm going to start with the simple, basic world. Is you have a payload or shellcode, and the payload does something. So it adds a user or it gives you a command shell or something like that. So that's the simplest. Well, that's like 1985 hacking. So you have a payload. So I'll talk about shellcode. With a payload, you usually want it to do something. Sometimes you don't want to make a connection back. Sometimes you just want to add a user. Sometimes you just want to like delete their hard drive. You don't care. You don't want anything. But a lot of times, if you're an attacker, you want some sort of interactive communication with the machine that you've attacked. I guess I don't know if I should explain what shellcode is, because I'm not sure if everybody in the audience. But shellcode is just the machine instructions that are going to be run when you're exploiting usually when you're exploiting a vulnerability. Or if you're attacking the machine, you're going to want to run some sort of arbitrary code. You might hear a lot of arbitrary code execution. So generally, this shellcode is what we're talking about when we're talking about arbitrary code. So we'll want to do something like start a command shell and then somehow interact with that command shell. So one of the most important fundamental things about a payload is making some sort of connection. So one option is that you can, the shellcode that's going to be run on the victim machine can connect back to the attacker. And that is what we would call like a reverse connection. Or you can connect to the victim, again, most likely. But, and that would be what we would call a bind. So those two are like the pretty basics, and there's not a lot of interesting things that I'm going to talk about with those. But FindSock is pretty interesting and has changed in the last couple of years. So that is being able to use the existing connection. And what I mean by this is, if you exploited some sort of program, you probably somehow, sent your data to it. So, example, FindSock wouldn't work for something that you were communicating over UDP. But say if you're attacking a web server, you already connected in over port 80. And now you've exploited this process. And you can most likely reuse that same socket that you've already had. And then you don't have problems with things like firewalls preventing outbound connections, firewalls preventing inbound connections. And it's also a lot stealthier in a network point of view. I mean, we've sat through several presentations about, IDS detection and stuff like that. So I'd be interested in any IDS that can actually do something about this sort of thing. So this is where we'd start with like an HTTP session and then turn it into like a command shell or something on the same exact connection. So we'll just talk a little bit about that and how you do that in some of the recent changes. So the first major technique we saw of this was what we call like get peer name. I believe that's the API, I could be wrong, but get peer name FindSock. And it was made popular by the group LSD, Last Stage of Delirium. And so the concept behind this is when you were sending your shellcode to the victim, you would connect to them first before you sent your shellcode. And then you would prepare your shellcode, and you would take the source port of the connection that you just made, and you would embed it in the shellcode, most likely in some sort of compare instruction or something like this. And then when the shellcode runs in the victim, it runs in a loop, just looping through 0 through 1,000 or something like that, and try to call get peer name on all of these file descriptors. And then it tries to compare the source port that it gets from get peer name. That might be the wrong API. I think it's get peer name. But and it compares it with the source port that you embedded. So then when you find something that matches your source port, most likely this is your socket. So the pros of this is it's a really simple idea, and And it's a simple implementation, and it works really well. When it works. So the cons is that it wouldn't work through something like a proxy, where your source port's going to be changed. So it's not going to necessarily work through a NAT. You know, it's not going to work through a lot of different network conditions. Maybe you're going through a reverse proxy or a web cache or like some sort of these sorts of things. And the source port may not stay the same through this, and then this technique is not going to work. You also need to embed a source port, which means that you may need some sort of more complicated exploit infrastructure, because now it's not just some simple send a payload that runs. Now you have to, you know, do something and modify or build the shellcode on the fly. I'll use the term shellcode and payload almost interchangeably. So. Okay, so then there's this new technique. It's not necessarily new, but it's gained popularity, I guess. So we used to do git pure name, and now we move to what we call find sock. So you still have to embed a piece of data in the code, but in this case, we're embedding a tag. Usually, in our case, we're embedding a 4-byte tag into the shellcode. Then you call receive in a loop, and then in order to avoid any sort of blocking issues or anything like that, on Linux, we're using the message don't wait flag to receive, which will prevent the receive from ever blocking. So then we can just sit here, loop through, and read data out of these sockets until, you know, we've hopefully read 4 bytes in, and this matches our tag that we've embedded. So the pros of this, well, it'll work through a proxy or NAT, because now it's not dependent on any sort of connection metadata, like an IP address or a source port or anything. It's now actually dependent on data that's sent over this connection. And it's still fairly simple and small to implement. So the cons, and this is things that we've addressed in our implementation of it. The data may be left on some sockets. For example, you know, you may, once you gain control, there may already be buffered data on the file descriptor that you're connected to. So this, and this also can be more timing sensitive because of this sort of thing. So then how we address that in our code is that we time it so that these, we always receive 4 bytes. So we're receiving 4 bytes, and then we basically let the loop spin for a while. So it just keeps on looping, and hopefully this will flush all of the data out of the sockets with these reads, and hopefully none of those are going to match our tag. So we sort of let it go and spin for a while, and it flushes all, and a while in computer terms is like, you know, a second. So we let it spin for a while, and it clears all the data out of the socket. And then we send our 4-byte tag. And this, and pretty much all the situations we've seen, works to a very high success. So I've never seen it really not work. So one problem then is this would be more complicated than Windows, because Windows doesn't have the equivalent of the message don't wait. So you'd have to do something like IO control socket to set the socket into non-blocking mode, or do you know, something like that. So that's one of the disadvantages of this technique. Okay, so does anybody have any questions? I guess this is sort of broken up into sections. So if anybody, I'm going to move on to something like completely different. So if anybody has any questions, go ahead and throw up my hand. Okay, I'll move on. So now I'm going to talk, I'm sort of evolving the shellcode here. So I want to bring up the subject of a NOP sled. So what are they and why? Often, especially in Unix, we don't know exactly where our payload is going to be in memory. We have a vague idea. So then basically what an NOP sled does is it gives us a buffer room in where we're trying to hit. We're trying to land in our payload, but we know that we can't hit directly on it. So this sort of gives us, that's the name sled. It gives us this large area that we can hopefully land in and then slide into our actual payload. And the bigger the NOP sled, the better a brute force will be, because you have this bigger target that you can try to hit. Okay, so now this is our improved shellcode. Now we have a NOP sled before the payload. So then, the NOP sled slides into the payload, and the payload gets itself. Okay, so some previous, most people have probably known NOP sleds as just the OX90 NOP instruction. And it's interesting there's a lot of IDS presentations here, because it's fun to rip on them now. So a lot of people have done this thing where they thought it was a feasible idea to signature on NOP sleds. Because, if there's an NOP sled, there must be an attack. So ADM Mutate came out with a program that did more random knob generation. And then I sort of worked on the same thing, and I'll talk about some of the research I did for that now. So this guy Optics released this multi-byte knob generator. And this is something that people have been trying to do for a while. I hadn't ever really been a good way of doing it. So this was capable of generating instructions from 1 to 6 byte long, and then plus additional prefixes. But it's still aligned to 1 byte. So you can still land it in anywhere, and it will still decode properly, and it will still work okay, even though that these could be like a 6 byte instruction. And the trick to this that no one else had been able to do was you build the sled from the back to the front, instead of from the front to the back. This makes things much, much easier. Once you think of it like that, like this is simple. So you prepend to the sled 1 byte at a time, and then you generate, and then the way his worked is that he generated a random byte and checked it against inserted cables. Is the instruction length too long? For example, if I only have 2 bytes on my knob sled, I can't use a 6 byte instruction. Is it a valid instruction? Does it have any bad bytes? Does it use any registers that I don't want it to use? For example, if I probably don't want it to ruin ESP, because I'm going to want that. Okay, so this is a demonstration of how a multi-byte knob sled would work. So I'm just going to sort of like go through here, and you can see, depending on where you land, that you would decode, this would be a 2 byte instruction, but if you landed before that, it would just be a 1 byte instruction. So these, if you land on this, you'll never even get to the DAA instruction, stuff like that. So this is just sort of the idea of what one would look like. Okay, so then OptiNop 2 is something that I wrote, and I'll explain how it works. So generating a random byte and checking it against tables is really inefficient, and the worst part about it is that it's hard to push to any sort of arbitrary distribution. So if you say, I want my knob sled to try to look like alphanumeric characters, or I want my knob sled to try to look like HTTP traffic or something like this, it's hard to do in this sort of like ad hoc testing approach. Another thing that you could have done was, instead of doing tables, was check it against the disassembler. But then it's the same problem as tables, and now you need a good disassembler. So what I did was I built some precompiled state transition tables. So basically what that is you pick a current first byte, a random first byte. It's going to be a 1 byte instruction, like OX90, for example. And now once you're on that byte, that's going to be the last byte in your sled. Now you want to pick the byte before that one. And I turned the problem into this, where you can just, for every byte you're on, you just basically have an array of 256 entries, and you have a table, and you can say, okay, now I'm on OX90, what choices do I have to go from here? And for example, one of these entries might be OX04, which would assemble into OX04, OX90, which would be add AL90. And along with that table, I have both how many bytes need to already be in the sled. So for example, this couldn't be the first byte in the sled because it's a 2 byte instruction. So I know that I already need 1 byte in the sled for this to work. And I also want to know that it's going to modify the EAX register, so I can prevent any sort of bad things. Prevent arbitrary registers from getting modified. So the cool thing about this is it's fairly language independent. The C version was 100 lines minus the tables. It's very fast, simple, and it's like deterministic. It's basically like a finite state machine. And it also, the cool part I think about it is it allows for very different scoring algorithms. So I'm probably going to speed up a little bit because otherwise I'm not going to get near anything. So it allows for a lot of different scoring algorithms, like I was talking about before, to try to match something to a certain distribution. Things it can't do, it can't support multi-byte opcodes, escape routes, things like floating point instructions. The tables are pretty large, they're about 124K. So here's an example output of what you would get with this generator. So if there's any IDS people out there right now who think that they have a good technique against this, I'd be interested to hear. So, and then I wanted to make sure that this was actually anything good. So I compared it with the ADM Mutate work. So then, this is a simple 1 byte view of the world. This is just byte distributions, like a histogram on a per byte level. So you can see that this is ADM Mutate. And I just did two runs. So these are just the same thing, just run twice to show that it wasn't some sort of, they're all pretty similar. So you can see that it's very heavy in certain areas. Like there's a lot of untouched byte space, and they only have the unique number. They only have 52 unique bytes in the sled. So then I did the same thing on mine, and mine has 141 unique characters. And you can see the distribution is hopefully even. You can kind of split it into two different groups, but it's hopefully evener, more even than ADM mutate was. And I can just, these are the two things again. So you can see they're pretty similar. So then I wanted to look at something more than just one byte, because I could just be, AB, AB, AB. So I wanted to make sure that I didn't have any sort of recurring patterns outside of a 1 byte view of things. So then I did the poor man's cryptanalysis, which is gzip. So then I compressed ADM mutate, and I compressed Optics' original version of this concept. His was just a proof of concept, and as you can see, it actually did worse than ADM mutate. You want the lowest compression value, because that's going to mean you have the best randomness. So ADM mutate actually beat Optics' original version. So ADM mutate had 27.3% compression for a whatever, a million byte sled. So then for my stuff, this is my program here, and then these are what registers I wanted to save. So in average situation, I want to save ESP and EDP. So I do that, and I get 12.2% compression, which is a decent amount. It's twice as good, I guess, as the 27.3. So then, and if you just wanted to save, for example, save ESP, you get like 11.7. If you want to save nothing, which is completely useless, you can get about 8.3% compression. So, so conclusion for that, the benefits is it handles restricted bytes and registers. So I can say, I can give it a list of registers and it for sure won't modify those. And I can give it a list of bytes and it for sure won't generate those. So I can get a list of all of the registers and it generates a perfect sled, but it's all like compare and test instructions and stuff like this. Things that won't modify any sort of registers. It's more versatile sled generation, like I'm talking about. So you could use it for things like knob stuffing. And what I mean by knob stuffing is, if you have a piece of code and you want to just inject garbage in between instructions, you can use this because then you can say, okay, these two instructions depend on each other because they use EAX in common. So just inject something in between them that doesn't modify EAX. Implementation and theory are simple. Possible improvements: support processor flags, 2-byte opcodes, reduce table size, stuff like this. So, okay. Does anybody have any questions about that?
Are you going to make these slides metal?
I guess the conference is doing that, yeah.
Okay.
So I'll
make sure you
put it on, yeah. So now I want to talk about something called encoders. So what are encoders and why? So I've been talking a lot about having to avoid bad characters, and that's because a lot of times in a certain vulnerability, it'll go through some sort of parser, it'll be in some sort of protocol, and there'll be some sort of characters that we can't have. Maybe we can't have new lines, maybe we can't have null bytes. So these are things that you can't have in your payload because it's going to, it's not going to work. It's going to, terminate or something like this. So we need to avoid bad characters. So the problem is usually you have to worry about this in every payload that you write. So it's like, okay, now I wrote a payload that's null-free. It was like, now will we have a situation where we have a payload that we can't have a new line? Like, I gotta rewrite a new payload now to not have a new line. So the idea behind a coder was that you just write a few of these, and then they apply to any shellcode that you write. And they're made so we don't need to worry about bad characters in the payload anymore. We only need to worry about them in a few encoders. So the way that works is that you encode the payload into a different set of characters. A common method of this would just be like an XOR, based on a byte, D-word, or a word, D-word sort of thing. You can do like an add, you can do subtract, any sort of mutation on this. And then you make a decoder stub that's going to get prepended before this payload. And it's just going to loop and decode this payload, the encoded payload, into its original value. So it's just doing the inverse operation. And then it just gets executed. So this is a way where you don't have to worry about this. And the cool thing about this is you actually oftentimes sort of like, well, now you have to prepend 30 bytes in front of your shellcode, so that makes your shellcode longer. You actually often save space because now you don't have to worry about any of these byte avoiding tricks in your payload. So your payload may ended up doing all these byte avoiding tricks and added 60 bytes to itself because it had to try to do things a little differently. So now we can work on just making the payload as small as possible, and then we sort of delegate the job of bad characters to the encoder. So now this is the improved shellcode structure. Now we have an offlet, an encoder, and then the encoded payload. So the offlet slides into the decoder decodes the payload does stuff. Okay. So now, because we have a decoder, it somehow has to know where the payload is and then unencode it. So this means we need what we call get EIP, or some way to get the instruction pointer or our current location. So I'm just going to talk about some of the methods that have come up for doing that and sort of why they've evolved and this sort of thing. So the simplest and the most obvious would be just to call to your next instruction and then to pop the register. Because this call instruction is going to push EIP onto the stack, and then the pop is going to put it into a register. So this takes 6 bytes, and this is the tried and true way that you would use in non-shellcode situations. So sometimes, and very often, you need to avoid having a null character, especially for vulnerabilities that are based around string operations. So this was the jump call approach, where you jumped to a call and then called backwards. So this allows your call now to be negative. So you don't have null bytes in your call anymore. And you can still do the same sort of thing, but now you just turn your jump into a negative jump. So now you can see there's no nulls in this anymore. And the NOP is a placeholder for where your shellcode would be. Usually you would put this call at the end of your shellcode, and then jump to it, and then you'd call back, and that would get you that way. Jump to call instruction, and now it's a negative jump. So this is something I think was really cool. And it was in an effort to try to find an alphanumeric get EIP. There's also many situations, well, there's also some situations where you may want to avoid OXFF. So the way that this works is that the fn set env instruction is an FPU instruction used mostly in exception handlers. And this will write some information to memory about the floating point, the current state of floating point. And one of these things will be the EIP of the last floating point instruction, not including the fn set env. So for example, I do a floating point divide, and then I call this. So then the location of this floating point divide is going to be written to the stack. And the reason we do ESP negative OC is so it gets written exactly where we want it in the stack, and then we say pop EAX. And now we have EIP in EAX. So we can do this in 7 bytes, and I think that's pretty cool. So like I said, do the last FPU instruction. The really cool thing about this, and I'll show later, hopefully, is it allows you to have much more permutations, because you just need any FPU instruction. So now you have these 2 bytes that can be a lot of different possibilities, which makes it harder to do signature. It is also it's smaller than a jump call, because as you saw, jump call is 8 bytes, and this is 7 bytes. So it's pretty cool. So this is the coolest of them all, in my opinion. I'll just give credit to people. FPU was come up by Noir, he works for ImmunitySec, David Tell's company. So then this came up with Gara and the rest of the core security guys. So what this does is it's a call $+4, as we call it, but a call instruction is generally relative to the end of the instruction. So this is basically a call -1. And you're going to call into the end of your own call instruction, and then decode from your OXFF. And you can see at the top, this is what it looks like before the call. And then when you call, you're going to land into the last FF of that call instruction. And now that return is actually going to be a inc EBX. And now you can pop EAX. So this is sort of a cool technique to avoid the jump call situation. And this was around before the FN set ENV. So I think this one's definitely really cool, and it's 7 bytes. And the annoying thing is that out of the FF instructions, there's inc, dec, and push. There's not a pop. So if we could have gotten, if there would have been a pop instruction, you could have done it in 6 bytes, and actually tied the real way to it. But we can't. So, but it's still definitely very cool. And you may be able to actually use this instruction to use this one sort of instruction you get out of this trick. So it can either be an inc, dec, or a push, and maybe in your shellcode that might be used somehow. Okay, so I'm not going to really talk about this very much, but people really want an alphanumeric get EIP. Because right now, in most alphanumeric situations, you work off of some sort of context where you say, I know EAX is going to point to my shellcode, I know EB, or something like that. So it'd be nice to have a generic way. So people really want it. People really want this. Well, so far we only found, I had nothing to do with it, but there's only been a way for Windows. And what you can do is you can just link in an exception handler, cause an exception, and then pull EIP out of the context record. And you can do this in all assembly instructions that aren't going to have non-alphanumeric characters. Okay, so that's all I'm going to talk about any sort of get EIP stuff. Does anybody have any questions on any of this? Okay. So now I'm going to move on to improving encoders, because most of the time you would have some sort of static decoder stub. And that's not good for IDS reasons and stuff like this. We want, yeah.
If you didn't have to worry about the size of the decoder, are there generators for that would generate more random things?
Yeah. So usually you have a static encoder, but that's not cool, right? So we gotta do something cooler. So I'm gonna talk about some polymorphic encoders here. So the first polymorphic, or one of the big polymorphic engines that got talked about was CLET, and it was published in FRAC. It generates permutations of decoder stubs, inserts things that will reverse operations like add 4, minus 4, stuff like this, not equivalent instructions. And all of the things are implemented in C and they generate themselves. The process is well thought out, and it was more of a paper than a tool. You could get mathematical output of it. It was very focused around spectrum analysis and this sort of thing. So it was pretty cool in that. The cons of it was that it's complicated and it's really hard to extend in an iterable way. The decoder generation wasn't that cool. And it was making compromises, it was compromising size for polymorphism. And that's something that I don't think you need to do. I think it's something that cool to not do. So I came up with what I call conservative polymorphism. And just to clarify, this isn't actually polymorphism in the virus sense, it's in our own sense. It's just generative permutation shellcode or something, but polymorphism sounds cooler. So what you do is you use the inherent variability in shellcode to add permutations. So the pros of this is polymorphizing code is pretty easy. There's no size or functionality compromises. And you actually, as an added benefit, you get bad character and register avoidances. So this is sort of an after effect feature. Cons, it's less thought out. They didn't actually even try this on any sort of IDSs or anything. So it's just sort of a, whatever, little thing. It's harder to push to arbitrary byte distributions. That's not something I worried about. And it's less polymorphism. Okay, so how it works is blocks are dependency graph nodes. So blocks consist of zero or more possibilities. And then you can do things like register pool assignment. For example, you can say move register 1 to register 2. And these register 1 and register 2 will be randomly picked when you generate it. So you can have a list of things. You can take things out of the registry pool, saying, I'm going to take ESP out of the registry pool, so no one is going to ever use ESP for when it does these allocations. So you get this gain robustness as a nice side effect. So the current implementation was a bit ugly. It's hard to do without writing a real assembler because you just have to build the instructions in code. But I wanted it to be fairly fast, and I'm too lazy to write an assembler. So PEX poly has 3 phases. It has dependency iteration and block selection, instruction offset calculation, because as these things get moved around based on dependencies, the offsets are also have to be recalculated. And then it has instruction register assignment. So I'll sort of, I have a diagram in a second, so hopefully if this is making sense, I'll make sense in a second. So it's too much to try to polymorphize every payload. So this is the same sort of thing tied in with the encoder. Now we can just do it once, and we can get it for all of our stuff. So I made one encoder called Shikaraganai, and it uses Noir's FPU get an EIP technique. And right now it has approximately 1.3 million permutations. In an average case, that's with only saving something like ESP. It does an additive feedback XOR, which means that instead of just, it does a D-word XOR, but instead of just XORing with the same key, it takes the D-word you just decoded and adds it back into the key. So there's key feedback. So your key's mutating across your entire decoding of your encode. So in total it's 27 bytes. 4 of those bytes are the key. 4 of those bytes are encoded because it actually will encode its own end of its decoder. So there's actually only 19 bytes that are somewhat static. And out of those are the 1.3 million permutations. So here's a graph of the dependencies, and this is what I'm sort of talking about. So if an arrow is sort of inverse, so if you sort of point the arrows backwards and you're pointing to something it depends on. So for example, this clear EAX move XOR length is going to depend on clear EAX. And the numbers before these are the number of blocks in this node. So for example, I can clear EAX in 4 ways. I can do an FPU instruction in 102 ways. And that's what I think is so cool about Noir stuff. So then basically, you have this dependency tree. Now you can somehow iterate it. So I can just basically pick a random one and say, okay, I'm going to do this one now, now I'm going to do this one, now I'm going to do that one. And as long as you meet your dependencies, you can sort of iterate through. That's one of the ways you get this polymorphism, is just by graphing out the dependencies of the instructions, because they don't all need to be in some sort of order. It's arbitrary what order it's in. So then by doing that, you can randomly shuffle things around. And then that's where you get in, you have to recalculate offsets. And then you also have to do, I also added to this, I do random register assignment. So if it's arbitrary which register I use, I just say register 1. So this is an example output. This is in like debugging mode, so it's not decoding its own end. So you can see that, you know, the Git EIP I was talking about before, and you can see the, you know, stuff like that. So I will sort of do like back and forth between two of them. So you can see that they, you know, change a bit, you know, the registers change, EBX which is ECX, and, you know, whatever. So, and then this is an example of what it would really look like since it decodes the last 4 bytes of itself. The last 4 bytes is garbage. So, so that's all I'm going to talk about that. So, does anybody have any questions? Any comments on how cool I am? I'm just kidding. So, yeah, I'm going to move on, I guess, and I'll talk about egg hunters, and I'll explain what they are and why. So, sometimes, so if you ever noticed, like, this presentation has basically been problem solution. Like, we came up with some sort of thing that happens a lot, and we have different solutions for it. So, sometimes we have a very small size constraint. For example, it's usually not enforced. It's usually we can write a really good exploit if we choose to make our payload space smaller. So for example, I may have a 10-byte buffer that I'm overflowing or something like this, and I want to do a partial override of the return address, because that's going to give me like super cool reliability. So this only gives me, you know, a smaller size. Say it's a 40-byte buffer or something like that. So I only have 40 bytes for my shellcode, and that's not going to fit any sort of shellcode. So, but oftentimes we can somehow put our code somewhere else in memory. We can put it in the HTTP header in our request. We can put it in some sort of auxiliary field. So our data will still be in memory somewhere. So what we do is we put our code in memory, and then we put some sort of tag in front of it to denote it as the shellcode we want to run. And now this small egg hunter runs and searches for our shellcode in the process memory, and then it executes it. We have a problem. We need to validate a memory region before we can search it. Otherwise, we're going to, you know, crash out the process, cause an exception. So this is the improved shellcode structure. Now we have the egg hunter, and this arrow somehow denotes that it goes out and finds the encoder. So I'll talk about stagers in a second. So now it's easy in Linux because we can sort of abuse some system calls. Because a lot of times when you're calling into kernel memory, when you're calling into userland APIs, you're just going to crash if you pass it an invalid pointer. But when you're calling into kernel land, you know, the kernel's not just going to crash when you pass it an invalid pointer. It's going to validate that the pointer you passed it was valid. And it's going to tell you if it was invalid. So we can sort of abuse some of these things. For example, in our Linux case, we use the access system call. So we pass it a pointer to a memory region, and it's going to come back and tell us whether it's valid. It will come back with an error, a certain error code if the memory is invalid. It will come back with a different error code if the arguments didn't make sense. In this case, they're not going to make sense because it's just random memory. The chances of it actually being valid is very slim. So Linux is easy, and it's been done for a long time. So Windows, it was harder. So Windows is harder. You can try to use the native APIs, the Windows system calls, for the same sort of thing. The problem is that Windows system calls are not meant to be static. And in fact, they're auto-generated, and they're very different for every version of Windows. So we originally had one technique that was using it, but then, you know, Service Pack 2 came out, and it was like, oh, okay, you know, now it doesn't work on Service Pack 2. That's not cool. And so we parsed all of the DLLs, got all the native API functions, and extracted the syscall numbers. It's pretty easy because these are all pretty much auto-generated. So the first instruction of all of these things are like move EAX syscall number. So we just disassemble them all, wrote a little script, and like pull out all the syscall numbers. So I got that here. So we built this Metasploit system call table. So we have all these system call symbols, and then all of the system call numbers for all the different versions. You can see NT, 2000, XP, SP3. So I can put in example, I'll say like OX, OC, and I'll highlight that. And you can see that this syscall number has changed a lot over the thing. So actually what we didn't know at first, and I didn't know until like Oded told me like, oh, you idiot. So I was like, yeah, like, I'm gonna do this, and we did like this cross-referencing, super complicated. It's like, well, they're auto-generated and they're alphabetically. And I'm like, oh. So it turns out that we can use NT-access check and audit alarm, which happens to be the third alphabetically ranking. And this, as you can see, is OX02. We highlight, and it has been static so far all the way across. So then the way this works is that this, I'll go back to my slides, I believe I talked about this. So, yeah, so something you want in these sort of, if it is valid memory, you don't want it to do something. So in this case, for NT-access check and audit alarm, you need special privileges for the API to work normally. But before it's going to validate your rights, it's going to validate the pointer you passed it. So we can pass the pointer. And it would actually take several arguments. And actually, the cool thing about this little table is that you can like hover over it. You get the, prototype here. So you can see this is some super complicated. All right. Well, the cool part is that it's passed through ECX. So ECX is like a pointer to the vector or whatever you want to call it. So all of these things are encoded in memory somewhere in a structure, I guess. And a pointer to that is passing ECX. And then this system call is going to verify that ECX pointer. So then, in this case, really simple to develop, verify a piece of memory. You push O2, which is the NT-access check and audit alarm. You put it into the EAX register, and before this, of course, you would, in the ECX register, you would have your pointer to the memory region you were trying to validate. And then you execute it, and then you compare the address. And if it was, we just test the last byte for trying to make things small, but it should be, pretty much 100%, this is going to be an access violation. And that means that this memory isn't going to be mapped. And if it's something besides an access violation, it most likely means that the memory is mapped.
Why don't you use SEH so you're not depending on system calls?
Because, as you can see, this is a whopping, 4 bytes. So, actually, let me pull out the, open some good editor here. Let's do it here. So, I'm not very, good with computers, so hold on a second. So this comes out to be, I think this is wrong. I think it's actually 31 bytes, but it may be 32 bytes. So our entire REcon code is 32 bytes. And that's the whole point of this code, is try to be as small as possible. So we do actually have a version that uses SEH, but it's larger than using something that doesn't use SEH. And you can see this is the whole code, it's tiny. We check the page, blah, blah, blah. We, whatever. And then, so this is the entire code to find ourselves. So, any questions? Yeah?
Yeah, you can use the hint instruction and then on the consent for and the at random speed and you use this central syscall.
But it's only for newer processors?
Yeah, but once that mostly run here.
Yeah, you should tell me about it later. I gotta keep going. But cool. So what you're saying is that you can use it was OX2A, the OX2A interrupt on Pentium 4 plus processors to do something similar to this. So that's also cool. We haven't looked into that. We didn't know about that. So cool. So now I'm going to talk about another improvement called staging. So, like I was saying before, it sort of applies to ACOMs. We often have size constraints. And sometimes we have size constraints and we can't actually find a place to put our code in memory somewhere else. So we can't really use ACON, or we would just like to avoid it. but the real cool reason for staging is staging extracts the connection mechanism from the payload. So what that means is a stager establishes a connection somehow to the attacker through one of these ways we talked about before, either find stock, reverse connection, or bind connection. And then the stager reads in on this connection more machine code. In this case, we call it a stage. And then it will pass the socket onto the stage and execute the stage. So then our new, sorry, that last thing should be stage, not stager. So the, ignore this slide. So, so we're now executing a hopefully smaller stage because it doesn't need to have all the functionality that we want there. It doesn't need to open a command shell. It only needs to open a connection and then read more code. So it's much smaller than native API or something. So we need to use like WS232, like the WinSock libraries. But function resolving is not something that you're going to be able to do in a small amount of code. And that's sort of the goal of the stager, is to be as small as possible. So what in the world can we do? This was actually another thing that Oded did. We presented it as Kensec. And it happens that he noticed that in WS232, many of the ordinals are static. And what the ordinals are they're like sort of the index. You say, I want this function to be revealed. And for the most part, these are completely like always running. Like they were never really thought of to be static. These are just, built. They're not any sort of predictable. And you can actually tell in the .lib file whether it's pretty static or not. So it happens that for some reason in WS232, I'm not sure of the reasons. And he actually noticed this because some things imported by ordinal instead of importing it by name. They have static ordinals. But unfortunately, not all functions have static ordinals. For example, you cannot call WSA socket. You must call socket, which means you can't directly pass our socket to, at least we think we can't directly pass it to command shell. We have to use a piped-based shell stage. So everybody has any thoughts on how to convert like overlapped I/O, socket and on, or whatever, in order to get this thing to work? Because right now we have to use like a piped stage or something like that. So the way this works is that we somehow have to find WS232 VLLAs. We can do this pretty easily. You just you like walk the peb. You find like we're walking the in order modules. I actually have also in here. I have the and then these names are going to be in Unicode. So then what we do is we kind of do this cool like hashing technique to try to find this, and we match WS232, and then we figure that this is their current base, and we can do it pretty small. And then once we have that, we can resolve our functions by these static ordinals we were talking about. So then you can see here, these are just some sort of static ordinals, like 23 is socket, 16 is receive, and 14 is connect. So I'll open this guy. Damn you Windows G-lines. This is just talking about the same sort of thing. There's a little paper I wrote. So here are some examples that out of the file that do have static. So this is just to give you some of these sort of functions. And things do use these static ordinals, so Microsoft couldn't change it because functions do link into these things by the way. And out of that, you can see in this thing, we got 93-byte reverse connect stager, which was pretty much before Oded came up with this technique, was unheard of in some sort of Windows shell code. So it literally would have been like 250 bytes or something like this. So this technique had been able to give us down to 93 bytes, which is pretty impressive. So I think I'm a bit early. I compensated too much. So I can talk plenty more about like a lot of this sort of stuff. There's a lot of interesting stuff in this that I can sort of ramble about, or I can expand further on any of these things that I've talked about. Does anybody have any ideas and they want to get?
Okay, with your earlier distributions of the obsolets,
right?
How it was very even.
Right.
What kind of enabling would you have to do if you wanted a less even distribution? Because I noticed that there was like a 3-to-1 ratio between certain things.
Yeah. Well, the cool thing I think about That's unique is trying to think if I have a
scoring.
I have a copy of it on my laptop. Um, so, can you guys read that, I guess? Whatever. So, like, I have this scoring function somewhere along here. And this is the entire code for the Perl version of the tables. So that's one of the cool things about it is, like, you don't have to worry about this stuff. You can see that the tables are, of course, like, super big. Like, So, anyway, the scoring is right here. Basically, what I do now is I wanted to try for the most even distribution I can. So I keep a count table, and this is just this counts thing. So every byte gets incremented when it gets used. So I just check, and I try to find the lowest count. If I find a bunch of things that match, I randomly pick one. But the cool thing is, this scoring part is these, 3 lines that you see right here. So these 3 lines are the scoring algorithm. So you can abstract this into any sort of different thing that you want to do. In fact, when we were at CanSec, Indian Empire, Chris Abab was talking about some analysis stuff. He was talking about bigram analysis or n-gram analysis. But it turns out that bigram analysis would basically work perfectly because you can basically turn it exactly into a weighted state transition table. And I already had a state transition table. So I'd basically be able to weight my states and decide the best way to do it. So you can basically very easily take in some arbitrary, some file, some web server log, or HTTP logs or something. Not logs, but HTTP data. You can feed it into bigram analysis. It would build this weighted network of the most likely things to occur in a certain state. So when I'm at byte 10, when I'm at H, T usually follows it in HTTP or something like that. So I can say, every time I'm at H, T should have a 90% probability of happening. So then I can just change my scoring algorithm. Another cool thing about doing it this way is that it beats the sort of random way of doing it before because this is very deterministic. So it allows you to do sort of I guess we could use a chess analogy or something, where you can look ahead and say, maybe this isn't the best choice for me to do now, but what sort of choices is it going to bring up in the future? So I can do recursive, I can do 10 choices out, for all of these choices, keep on going down. And then I can score this in a grand sum. I can say, wow, it's even though, A has been used a ton, it's really best for me to pick A now because it allows me to get Z, and Z's never been used yet, and Z is really high in, my probability weight because I'm using the ZZZ protocol or something, you know what I mean? So I think by designing this thing, in this sort of state transition, you've enabled yourself to do a lot of these things. So I was actually very much aiming for the most even distribution I could. And I understand that that's probably not what you want. But it was just sort of a concept that I needed a goal, and I didn't know what to be trying for. So I just said, well, trying for evenness is probably something that's pretty fair. So back to my slides. I'll go on sort of get my table of contents so people can see what I've talked about, if anything else they wanted to. And I'll just go quick show for the analysis what he was talking about. Was this table of evenness, as you can see. It's bad because you have all of these zeros and all of these non-zeros. It's not something you'd want. It's almost better to have. In fact, before I tuned it, I had just complete randomness, and I was like, well, that's almost probably better because this would be very easily signaturable because it's very predictable. You can even break things into the groups. Because the groups are even almost like blocks visually. They're the 11s and the 12s, right? And then there's the 39s, the 39, 3A group, right? And there's basically, and then there's the 0 group. So you basically break it into 3 distinct groups. And that's probably not a characteristic you would want. But then again, when I put it through gzip, it didn't seem to be too smart about that sort of thing. So and someone could definitely signature, you know, some sort of specific intricacy of this, then it's, you know, it's a lost cause because you can just change it, like the concept. You can add some more instructions in case I missed any. I mean, you can change, you can easily change the scoring algorithm to be your super secret ninja scoring algorithm. It's going to be completely different, you know what I mean? You could emulate, you could have like ADM mutate compatibility mode, you know, or like, so, yeah, I mean, but it's still, there's some things you can't do. I beat over 50% of the byte, like 128. I wanted to get more than 128 unique bytes, and I got 141. And I'm trying to see if that's a lot. No, okay, there's that. So yeah, I have 141 unique bytes. And you just can't really do that much after that. I mean, you have the limitations of the instruction set. I can't make, you know, privileged instructions become unprivileged or something like that. So this is sort of, I think, the barrier, at least for the stuff I'm going to work on, in terms of sort of doc research. So, back to the table of contents. I wish I could like have something to demo, but I could demo this stuff, but you can't really see any of how it's going on. I mean, it would all be really transparent. Yep, it found the shell goes to memory. Like, I can't graphic search it. So I think that was about an hour. So, anybody have any other questions? Okay, cool. Thanks, guys.